There they are, waiting patiently. Ridvij, what's up?
Nothing much, just tired.
From playing too many games?
No, I just spent the whole day building my new desk.
Oh, let me see.
Yeah, oh, hold up. It's like a really L-shaped kind
Ah,
of desk.
did it come like in a box in like UPS or something?
Yeah,
Where's it from?
it's from Office Depot.
Ah, nice. Nick likes your desk too.
Thank you. You can't see it very well, but
Oh, he's in it. Are you, wait, is it the Millennium Falcon?
Pretty much, yeah.
Ah, very nice. Very nice. You can see I have the same picture behind my head every night. I sit in the same spot on the couch. Yeah. Yeah, I'm predictable that way. Same with restaurants. If I find a food I like, I'm just like, yeah, I'm not going to try anything new. Same thing all the time. Total creature of habit. I don't, maybe I got that from my dad. I don't need to try new things. If I like something, just the way it is. Who else is here? No one else wants to show their faces. Come on. There we go. There's not much. And you?
Dealing with a lot because I enroll tomorrow, and
Yeah.
sometimes they'll let you. There's like a problem where if you want to enroll, you need a prereq. So, for example, I need to take a class 351 to get into 2 other classes.
Yeah.
And sometimes you can concurrently enroll in those, and sometimes you have to get the professor's permission.
Oh, yeah, because the grade hasn't posted yet.
Yeah, so I've been emailing back and forth, and the only problem is with your counselors right now. They can't really get to you that quick because I'm sure they're receiving tons of emails.
Oh, yeah, they're probably totally swamped.
Yeah, I got the okay from my professor that I'm in because I already have a class with him this semester, and he knows my name.
Right.
So, like I have like pretty good relationship with him. So I emailed him. He said, like, yeah, that's fine. If something happens, email your advisor, and then they'll reach out to me. I'll give them the okay to enroll you. So he pretty much gave me the clearance.
That's cool.
Just making sure that he said to email her because my enrollment's tomorrow. He said to email her tomorrow if I have any problems. I'm like, I'm gonna get it a day in advance just in case.
That's interesting.
I send it out. So now it's just kind of a waiting game. And I know sometimes if you enroll into that class first and then go back and enroll into the other ones you can get in, just kind of up in the air. So I just got to make sure I'm on the wait list for those ones in case I.
Yeah, that's nice. Cedar, what's going on?
I'm drawing as I wait to start. So I have a commission.
You're drawing something?
Yeah, I got commissioned.
Ah, what do you get commissioned to draw?
An icon kind of say for a friend.
So when you say you got commissioned, does that mean coin?
They're paying me, yes.
Yeah, that's the best thing, right? When you got skills, you should get paid for those skills.
Yep. I can share it right now if you want to see it.
Yeah, I'd love to see it.
Oh, I can't because host has it disabled.
All right, how do I do that?
I don't know.
Here you go. You're the co-host now.
Sure. Yeah.
Check it out. Oh, nice.
This covers my thing.
So what are you doing that on?
I use Clip Studio Paint.
Interesting. So you're using a stylus kind of like when I draw, or what do you?
Yep, I have this.
Interesting. So are you also like an art major too?
No, I'm a math major.
No, nice. Well, that's cool. That's very exciting. Very cool. Anyone else not working on anything fun? I see that 29 of you are here, so that's cool. Who can I pick on? Samuel, what's up? How you doing? Samuel, I know you're there. Do you not have a microphone? You want to chat? Oh, doesn't want to participate. Samuel. No. Oh, he's typing. Hello. All right, there we go. That's good. I see you're out there. That's cool. Oh, so you guys had asked, somebody had asked about posting grades. So I went into the titanium thing and tried to figure out how that grading thing worked. Yeah, I have a PhD in chemistry, not in figuring out how titanium's grading option works. I, for the life of me, couldn't figure out. So what I'm going to do is I'm going to show you how you can figure out what you have to this point, assuming you've kept track of all the numbers you have. If you have all the grades, which you should be able to calculate the grade, because this is how I would do it. If you don't, I can just do the math for you and email, but it's always useful for you to be able to do the emailing on your own. So let me just pull up a sheet. Okay, let me just close this. All right, so let me share my screen. Oh, come on. Okay, so you can see that I've got an Excel spreadsheet up. Y'all can see that. Okay, so here's how this would work. So you should have homework. Yeah. You guys can see my screen?
Yeah.
Quiz 1, quiz 2, quiz 3, exam 1, exam 2, right? So those are the only things we've had so far: homework, quizzes, and exams, right? And normally what I would do is I would just use Excel and print out a formula, right? So what we said was that homework was going to be worth 25%, which is, I'm just going to write this down here.
Can you not? Oh, sure. Yeah, pull it up.
25%.
Pull the bottom part. Like throw the whole thing over the top, and then pull the very bottom layer.
Somebody needs to mute. Anyways, okay. So homework we decided was 25%. The quizzes, now I have to go back to the syllabus because I totally forgot.
You need more?
All right, no, not the roster.
Take one.
Yeah.
Take here. What do you mean? I'm laying on 3. There's 2 right there, and then there's another one over there, but it doesn't have a pillow sheet. So
Somebody needs to mute. We're hearing your private conversation.
sorry.
No worries. I don't care. It's just kind of awkward. Chem115. You know what? I'm going to waste my time trying to find it on my desktop. Let me just go back to here. All right. So here's the syllabus. And much easier to find it that way. Okay. So on the syllabus, you'll recall that the exams were worth 40%. The final exam was worth 20. We've only had exams right now. So I'm just going to say 60% of the grade is exams. 15% is quizzes. So that's 75. That leaves 25% for all this other stuff. And I was just going to use your homework for that score. All right. So that means quizzes, overall, the quizzes are worth, I totally forgot again, 40%. My brain is just not working. What did I say? Quizzes are worth 15%. All right, so quizzes are 15%. Actually, let me add a couple columns here. This will make life easier. Oop, I didn't want to do that. Let's see. Insert. Insert. All right, so this is, let's just call this quiz average. All right, and then we'll call this exam average. So I'm basically showing you how I would calculate your grade. So let's say on the first, and let's say what the values were. So we'll just do real numbers. Quiz 1 was worth 20 points. Quiz 2 was worth 30 points. Quiz 3 was worth 30 points. Exam 1 was 100. exam 2 was 100. Okay, so let's say this is some person, right? Let's say I went into Sapling and I found out your homework was a 95, all right? And let's say on quiz 1, you got, I don't know, let's say you got a 17. And let's say on quiz 2, you got a, let's say you got a 27. And let's say on quiz 3, you got a 29. All right?
Are you dropping any quiz grades or test grades at all?
The syllabus says I will drop the lowest quiz score, and so that's still going to stand. At this point, because you still have some to take, I'm not going to drop one. So you can do this math by dropping one of them, and then your average will only have 2 quizzes. So, yep, I will, but I'm going to wait until the end. Exam 1, let's say you got an 88 on exam 1, and let's say you got a 90 on exam 2, okay? So what I would do is, Excel is really simple. I can just do this, and I can go average. So it puts the average in that box for me. I can do this, click average, and it puts the average in that box for me. All right, so this is the average of your quizzes, which is what I will use. That's your quiz score. This is the average of your exams, right? So that's what I would use. And then in this last box, I'm going to put a formula, and that formula is going to say equal. So that's telling it wants a formula. It's going to equal this column times 0.25, right? So it's going to, it shows you the formula up here. It's going to equal that column times 0.25 plus the quiz average times 0.15. We said quizzes were 15%, plus the exam average times 60%, 0.60. And if I hit return, I did something wrong. Oh, because those are all numbers, I have to divide that whole thing by 100. Normally I use percents / 100. That doesn't look right either. 25%, 15.
I think you forgot the point for the 60.
I
think
forgot.
60, and then it's supposed to be 0.6.
Point. Oh, asterisk 0.60. 0.60. Thank you. You guys are better at this than me. Boom, there it is. So what is that? That's an average of 0.808, which is actually, I guess I didn't have to do the divided by 100 then. So let me just go back to this formula. I don't need to divide by 100. 80.8. So that person, whoever that person was, has an 80.8. So then I would go back to the syllabus and I would say, okay, what's an 80.8? And 80.8 in this is right in the middle of the B range, so that would be a B. So whoever this person is solidly getting a B, all right? By the way, I got an email today from the department chair, and I'll just share that email with you because it's much easier than just trying to explain it. All right. Nope, that isn't it. So maybe it's in my other one. Let me look here. Here it is. All right. So this is really important, and you guys want to pay attention to this, but I don't know that I have the authority to just forward this email to you. So here's what we've got. So this came from Cal State Fullerton. This is from all the people who are really important to know. So the credit, no credit grading information. Please read this as you'll likely be getting lots of questions from your students. So passing grade for an undergrad class is set at a C- or higher. So I'm suspicious that I just grade the class however I grade it, and I insert a grade for you all. You behind the scenes have to go in through your portal and decide if you want credit or no credit. And anything that you get that's a letter grade C- or above will automatically give you credit. Anything that's a C- or below, you will not get credit for. So if you're going to take that decision to take the credit, no credit, you will get credit if you earn a C- or above. So if we look at my syllabus, a C-, right, would be, according to this scale, 55 and above is a C- because it's right at the edge of the C scale. So you would have to get 55 or better to get a passing. I personally can only talk about Fullerton College. I don't know what the implications are at Cal State Fullerton in terms of, will this affect your ability to take an S class? Or pass, no pass, or credit, no credit certainly can't impact your GPA. But I think a lot of you are doing really well in the class, so I think you'd want to get the grade that you're actually getting in the class, right? So that's something that you can think about, but it turns out that you have time, right? You have until May 8th to decide about withdrawing for the course. And I believe you can do up until it. Now, it doesn't say in here, but I believe somewhere I read that you can select the credit, no credit for quite a while after our course ends. I think, yeah, the deadline for students to select this is June 1st. So if the class is done, you take the final exam, you're like, oh, dude, I don't like the grade I got in this class. I don't want a C-. I want credit, because then no one's going to know what I really got in that class, right? Boom, you can still do that up until June 1st, right? So I'm not 100% sure these have been posted anywhere for you guys. My department chair only asked me to share this information with you, so that's what I'm doing. What I probably can do is, because there's some stuff in here about how they want us to grade, so I think that that's probably not things I'm supposed to be officially sharing with you. I think this is the most important thing, C- or higher. So that's what you really need to know. And that, again, corresponds to a 55 or above, right? So if you're in that boat where you're thinking, I want to take this class, credit, no credit, I got other things I want to do, I don't really want to spend a whole lot more time worrying about your class, Dr. Hartmann, I just want to take what I got, that's cool. But remember, this class is, for most of you, this class is not, I just want to take this class because I need chemistry. You're taking this class so you can learn material that will help you be successful in the next class. And so that's something you really got to think about. Why are you taking the class? And is there a benefit to you for going credit, no credit? And so I can't make that call for you. I can talk to you about it, but I can't necessarily make the call. They have been. So Cedar posted that stuff has been posted. So good deal. Okay. So any questions before we move on to some other stuff? You guys all doing okay? I only see like a couple of you. It's just shy about turning those cameras on. It's weird. No one else wants to show me their face? No. All right. There you go.
I got a question.
Yeah.
What if we want to take chemistry in the summer?
Mm-hmm.
How would it work when we're like signing up for classes in the fall? Would we? Because I know we can't sign up for the class ahead, like for example, 121 or 120B.
Well, so you mean you want to take 120A in the summer, but then you'd want to sign up for 120B in the fall?
Yeah.
Ooh, that is a good question. I would think you might be in the same case as you would be with Andrew, where you might have to contact an instructor or you might have to contact the department head. So the person whose email I was just reading, his name is Peter DeLizer. He's the chemistry department head at Cal State Fullerton. So if you were to email him, I think it's just pdelizer@fullcal.edu. So if you were to email him, he could probably help you understand about what would happen if that was the case. I can't advise you on that. What would happen at Fullerton if a student said to me, look, I want to take this class, my registration day is today, and I want to make sure I can get in this, and I'm taking this class this summer, they would get a petition and bring it to me. They would get a prerequisite challenge form, and they'd have to bring that to me as the dean, and I would sign that prerequisite challenge form with the understanding that they were going to take that course, because if they got in the course, they'd get in the course because I let them. But as soon as the semester started, admissions and records would look for that prerequisite grade. And if they didn't have it, they would get dropped automatically. So they'd get dropped behind the scenes. So admissions and records would take care of that, not me. So I suspect there's probably a petition form somewhere in the Cal State system. I just haven't been here long enough to know what that is. Sorry, Sarah, I wish I could give you a better answer.
Oh, it's okay. That helped. Thank you.
David, I see you have a hand raised via your iPhone.
Yeah, I have a question.
What's up?
I know it said like for undergraduate courses, it would be a C minus or higher or
Yep.
below.
Yeah.
And then for actual like the courses like for major courses, those
Mhm.
would be a B minus or higher.
I think any class that's considered an undergraduate class, the way I read that email, it said,
Mhm.
I would think it's any course that's considered an undergraduate course. Let me read it again. Passing grade for undergraduate classes, doesn't matter if you're major or not. And the reason they write undergrad is, of course, because they have graduate programs at Cal State as well. So the passing grade for a graduate course is higher.
Oh, okay. Okay, that was my
Is it still a factor? But if you choose to credit, no credit, your GPA, yeah, your GPA remains the same. But one thing you guys want to consider, and I think the feds are relaxing them, but if you're getting any sort of financial aid, there were always implications about financial aid in terms of taking courses, credit, no credit, taking withdrawals and other things like that. I'm pretty sure based on what I can say from Fullerton is they've relaxed a lot of those guidelines in terms of financial aid. And they're doing a lot of stuff. If students withdraw, they're refunding a whole lot of things. So I think they're trying to work with you in this. And if you're thinking about transferring to another Cal State, you should be okay. The UCs are being pretty okay about transferring and things like that. UC's got their nose up in the air all the time, and they're really funny about their rules. But even they're being a little bit more conscientious to help you guys as students to get through some of those things. You're right. Changed from what? What, Brian? What's your question? Changed from what? Your GPA. Oh, yeah, right. Your GPA. So if you every time you take a class, your GPA goes up or down depending on how your grades do. But if you take a class credit, no credit, those credits don't factor into your GPA. They'll show as credits that you've taken, but they won't be used to calculate your GPA. And that's typically the case with courses like that.
I got a question.
Okay.
So since summer is going to be online now,
Yeah.
Did everything get switched over to fully online instructions when you go to register for?
You know what? I don't know, because I can only speak from what's going on at my school, and I haven't heard because I'm not teaching in the summer, so I don't know if I've gotten any of those emails. I suspect it's going to be just like this. I would hope that it's going to be remote instead of totally online, especially for science classes. We haven't heard yet. We're still planning on meeting in summer in Fullerton College, but I would say probably within a week or two, they're going to make the call. And if I had to go with my gut based on what everyone else is doing, they're going to have summer be remote as well. But a number of my faculty have already said if we go remote in the summer, we're just going to cancel the classes because we don't want to do majors classes with labs remotely. They're doing it now, but they're not happy about it. They really want to have those interactions. So like Bio 170, which is organismal biology, they're like, no way, we're not doing that remotely. The chemists actually surprised me. They're all jumping on board with Labster and remote and putting together labs in a box and sending kits out to students. And so chemistry is actually going to go ahead, I think, and do some of theirs. Anatomy and physiology said not a chance. They're not doing anatomy lab remotely, and they're not doing it online. I don't know. I think my anatomy instructors have this reputation of being super, super mean and hard, and they kind of like it that way. And so they're like, no way, screw that, Rich. We are not doing lab online. Yeah. What's up, Andrew?
I heard that some universities are actually considering fall semester being online.
Yep. It's going around. I mean, I don't know if you've paid attention. I don't, because I don't really listen to local news very much, but apparently the governor is warning people that, this may be the new normal till spring 21. And so they're not, no theater, no big groups, no movies, no sports, no whatever. I can't see Americans putting up for that for too long, because I think they're just getting answered like, whatever, if I get the bug, I get the bug. I'm not staying in my house for another year. It's just not going to happen. And I kind of wonder about that, because honestly, I don't know anyone. I don't have a big circle, but I don't know anyone who's got it. And it's interesting, just when I do go out, I mean, yeah, people are wearing masks now, which they weren't before, but people are out, they are. They're not staying home. Maybe you guys are because you're staying home and studying, but if I go to the store or something, there's people everywhere. Not as much as normal, but I cannot imagine most Americans doing that. But and I don't know. I mean, remember, I'm the one that said I didn't think anything was going to happen, and here we are meeting via Zoom. So it is kind of it's weird. It's weird for me being home. I don't hate it. I actually, because normally when I don't have stuff to do if I'm not signing papers or in a meeting, sometimes I'm shuffling papers or trying to find things to do. And today I spent a couple hours pulling the engine apart on my truck, figuring out that Cummins. All the push rods are bent, by the way, so that's interesting. There was a small washer. I don't know where it came from, but it got jammed between the timing gear of the cam and the injection pump. There's a little chip on the injection pump gear, but it still looks like the timing is right. So maybe I dodged a bullet. I don't know. No pun intended. I'm going to get some new push rods, which aren't expensive. Yeah, it's really hard to crank over now because all the valves are closed, so it has huge compression. So I got to pull the injectors out and see if I can't crank it over. But honestly, it's not as bad as I thought it would be. It took a while. I had to take the bumper off the grill, the intercooler, the radiator, the air conditioning, all that stuff came out, but it came out pretty easy, which I'm not used to. I'm used to cars being totally rusted and nothing coming apart easy. And here in California, this is like a 30-year-old truck, and all the bolts came loose, nothing broke. It was just like amazing. So got that going for it. So who knows?
Professor, does that year have a def box in it?
No, it does not. The 97 does not have. It's a total mechanical engine. There's no computer. It's not common rail. As long as there's power to the fuel shutoff solenoid, and even if the power goes off, you can just wire it open. So yeah, once it runs, it'll never shut off. That's another reason why I like that engine. It's totally mechanical. There's not a single computer in it.
Can it roll coal? Do you know what that means?
Yes, I do know what it means, and it may very well roll coal when I'm done with it, because it's totally stock right now. It's a big engine, and it's only rated at 180 horsepower, but you can get an extra 100 out of it super easy by turning the boost up, turning the injectors up, getting rid of the EGR. Yeah, there's a bunch of stuff that I plan.
It'll give you something to work on.
Yeah. Perla, I see your hand up. Are you wearing your love earrings today?
No, I'm not. I'm wearing hoops. I was wondering. I was wondering if how do we get the homework average? Is it on Sapling?
Yep, it's on Sapling.
Okay, thank you.
Yep, it should tell you. Are you wearing like a hat with ears?
Oh no, I have I put little pigtails.
Oh, I see.
Yeah.
Oh, very good. Was there another hand? Chris, did you have a question? No, I thought I saw someone else's hand up.
I had a question real quick about 120A.
Uh-huh.
It's 5 units, so what would we do for the 2-hour laboratory if it was online for next semester?
That's a good question. If it's online, they're going to have to find a way for you to do the lab virtually. And so there's a lot of people out there. I mean, I get emails like once every 2 or 3 weeks from some company trying to hawk their online software. Like this guy calls me nonstop about, hey, Dr. Hartmann, I know you guys have anatomy and physiology labs. Would your faculty be interested in looking at virtual anatomy labs? And I'm trying to be nice to this guy, but eventually I just got to tell him, dude, look, my people don't want your stupid online anatomy, right? So there are tons of companies that have put out virtual labs. One of them is called Labster, and that's been made available to the California system. I know we have it for free. I don't know if Cal State's, they probably do. So there are ways to do lab. The problem is, especially for me as a scientist, lab is really about learning how to use your hands, to be tactile, to learn to do things physically. And you miss that. And that's why I know a lot of my faculty are like, I do not want labs, because virtually, yeah, you can see things, we can make things up, things can even go wrong, but you're not using your hands to interact with real life things. And so they don't want to put their stamp of approval on someone who has had that virtual training. If Cal State allows labs to go, the labs are going to have to be virtual. That's just the way it is. And I'm not teaching in the summer, so I don't know what they've picked. But hey, who's this? Rookvij, my 30-year-old 364K still runs as smooth as the day we got it, because, well, okay, it's a Toyota. I give you that too. What is 30 years old? What is it? Is it just a Toyota T100 or something? He's typing. So I can't say what they're going to do this summer. Sorry. But if you're going to take it, you might as well. You might as well. T100, T200. Okay, yeah. Any other questions? I'm looking at the chat and looking at you guys to see if there's any hands up. Okay, then I think what we'll do, I kept you guys the whole time last time, so I'm not going to talk full 2 hours today. I think what we're going to do is go through some PowerPoints, and when it gets to be close to 6:30, 6:45, I'm just going to call it quits and let you guys go and work on some other stuff, because I know that that's totally not my thing. I don't want to, I mean, obviously I can do it. I talked for 2 hours and wrote, but I don't know if that's fair to you guys to do that entirely. All right, so let's try this. I'm gonna go to my thing. I'm not sharing my screen yet, so talk amongst yourselves while I get the PowerPoints for today ready. And what I'm going to try to do is I'm going to try to get them through my iPad. We're going to see how that goes. All right, so let me get this thing going. All right. And let me go to, let me share this. I'm trying to share it. I'm not sure why. Oh, there we go. Send a copy. Do it this way, airdrop. This might actually work. All right, here we go. All righty. Let me go back to this. Let me go to any conversations. Let me go to share my screen. And boom! Oh, did that just happen or what? Sorry, I amaze myself at my ability to do technology. I'm really an old school person. All right. Somebody asked me if I was wait, is Min Sung? Min Sung, you out there, buddy? Min Sung, talk to me. You skipping class today? Min Sung, where are you? Min Sung. Min Sung. Let me look at the participants and see if he's manage participants.
Question.
Yes.
Do we have anything to practice for exam 3 next week?
There is the one thing that was at the end of, I pointed it out last time, it was at the end of chapter, let me go back to sharing my screen, I'll show you. We didn't have enough stuff to get through it, and I'm pretty sure the exam's gonna be a little bit later, so I'll post some more practice stuff after today. But let me go back, let me share my screen again.
So you're gonna push the exam back?
Yeah.
Oh, okay.
I think we need to have a little bit more time, unless you guys are really gung-ho to take the next exam.
I mean, the sooner I know, the better, because I have another exam next week, so I have to prioritize my.
Okay. Well, I personally feel like next week Thursday is not the best. I would prefer to put it off one more week so that we can cover a little more material. So why don't I just make that call right now? Let me pull up my calendar.
Professor?
Yep.
So we have 2 more exam and then 2 more quizzes to go, right?
We're probably only going to have 1 more quiz and 1 more exam, and then just the final. I don't think we have enough time because we lost some time, and I think I'm going a little bit slower to make sure everybody's got everything down. I don't want to rush things. So next week is April 23rd. I think we should plan on April 30th for the 3rd exam. And then The 14th is the final exam. So what probably we'll do is we'll have April 30th will be the next exam. We could potentially have a quiz on the 7th if you want, or we could just have the final exam on the 14th. So maybe we've had 3 quizzes already, so we don't necessarily have to have another one. And even if I just have 2 quizzes, I'm not worried about that. So are you guys okay with having the exam on the 30th? You can shake your head. Yes. You can put something. So the exam on the 30th, potentially a quiz on the 7th, but not likely, and then the final exam on the 14th. I'm looking at the comments. I see a yes. 1 yes. Chris and Diane have voted for everybody. Okay? So that works? Marlo, does that work for you?
So the quiz would
Yes,
be
that's
after
perfect.
the exam?
Potentially. If we had it, it would be after the exam, yeah. Because we'll continue to cover new material between when we stop and when you take the exam, right? So if the exam is in 2 weeks on Thursday, we would probably stop with material for the exam 1 week before then. So we'd have like 2 weeks of material for the quiz. But I'm not sure that at this point, that's the best thing academically for you to spend an hour taking another quiz. It might be better for you and us to spend time together answering questions about the material. But I'm amenable if you want that quiz and you're like, oh my gosh, I'm seeing yeses from a number of people about that. So you can always message me privately and say, you know what, I really think we should have another quiz, and I'll consider it for now. You don't want everyone to hate on you, right? Oh, you want another quiz. What's wrong with you?
So it's 1 exam, 1 quiz, and 1 final, correct?
Yes, most likely that's the scenario. Yeah.
Okay.
All right. Okay, let me go back and I will share my screen again. And iPad. Okay, so here we are. I've got to remember that I'm using my computer's hot. Using my iPad and not my computer. So we started. Look at that. You can have liquids and foods in class now. Ah, how much better is that? You could even have adult beverages if you're old enough. You're not old enough. I know that.
I turn 21 next week.
What, really?
Mm-hmm.
So you potentially could have adult beverages. Okay. What's an adult beverage?
Coffee.
Adult beverage is slang for alcohol. Okay, electron configuration. So remember, last time we talked a little bit about some of these things. We actually didn't talk about these specifics, about this terminology, but I can throw them out. And remember, we spent a lot of time talking about the periodic table last time, and I find that's a little more valuable because the periodic table is what you're going to use a lot. Granted, the underlying reality of the periodic table is how electrons fill in atoms. The rules that are on this particular page, I'm not going to ask you to memorize these rules and regurgitate them. That's not important. But I think part of the reason that's behind how we put electrons in and why they fill certain energy levels are explained in these terms. So the Aufbau principle, we sort of mentioned this a little bit when we said that when you're putting electrons in atomic orbitals, they always start at the bottom, closest to the nucleus, and then they fill moving out from the nucleus. And we talked about filling n equals 1, then n equals 2, then n equals 3, the various energy levels. My pen just wants to write sideways, and that's a pretty big ink blob, right? So if you start at the nucleus and move your way out, and that's essentially what this is saying, but it's also saying that within an energy level, so I'm going to write down here at the bottom of it a little bit. You might remember that when n equals 1, you can only have s orbitals, right? When n equals 2, you could have s and p orbitals. And if you're thinking about the periodic table, that s block was only 2 across. The p block was 6 across, right? And again, the reason for that has to do with the underlying reality of what S and P orbitals look like. An S orbital is just a sphere, right? But P orbitals look like donuts, and there's 3 of them at any given energy level, and they're oriented along the axes. So if you had a Cartesian coordinate system, those orbitals would be oriented like this, right? And remember last time I said we don't know how electrons are moving? These orbital shapes seem to give the idea that an electron is like moving in its figure 8, which is not doing, right? What you should think about when you think about orbitals is you should think about like a container, right? So like a Tupperware container. So this S orbital looks like a sphere, right? And if you're talking about an S electron, what you're basically saying is that there's a good chance that that electron is in that shape somewhere. Where is it? I don't know. It's in there somewhere. How is it moving? I don't know, but it's moving within that space, right? It's just moving in there. And you don't have to worry about how it's moving. What is the significance of the P shape, the P orbitals? So these are P orbitals. We would call this the PX, by the way. This is the PY, and this is the PZ, because it's on the Z axis. The electron's not moving in that shape, right? It's just a region where you have a likelihood of finding an electron. And again, I can't explain why they look like this. Why is this what a P orbital looks like? It has to do with the quantum mechanical nature of the atom, right? Electrons hate each other, and this is how nature decided to get them in the atom and keep them as far away from each other as possible, all right? But what we didn't mention last time is that these orbitals are all equivalent, right? They look different, but they're just oriented differently. One of them is on the Z-axis, one of them is on the X-axis, and one of them is on the Y-axis. The S orbital, well, the S orbital is just oriented along the center of the XYZ. It's just centered right there, right? But what you might not have noticed is that if this is the S block and it's 2 across, what the implication is that an S orbital can hold 2 electrons. The P orbitals, there's 6 across. The implication is that P orbitals can hold 6 electrons, but the reality is there's 3 of them. So how many can each one hold? Well, if this can hold 6 electrons, but there's 3 of them, that means each one of these can hold 2 electrons. So I can put 2 electrons in that one, I can put 2 electrons in that one, and I can put 2 electrons in that one. And so when we start at the nucleus and start to throw electrons in, they fill in a particular fashion, right? And we end up with something called the electron configuration. And that's really only important for our perspective in terms of where do we end up when we end the atom? Where are the outermost electrons? Where are those valence electrons? But this Aufbau principle says you start at the middle and work your way out, all right? And then there's these other rules that we didn't talk about yet, but we need to talk about them now. This rule here basically says every electron is different, right? They all have different addresses. We're not going to talk about quantum numbers just because I think that that's beyond the scope of this course. There's other things that are more important, all right? This one's actually sort of important too, and it uses terminology that I suspect will be kind of foreign to you. This word here, degenerate, we're probably used to thinking degenerate meaning someone's a bad person, but in the case of chemistry, degenerate means they're equivalent in energy. So this orbital here, this orbital here, and this orbital here, they're all p orbitals, they're degenerate, right? That means they all have equal energy. So that means if I put an electron here or here or here, there's no difference. They're all identical, right? And so what that's going to tell us is that when I start putting electrons in, I'm going to put electrons in one in each of these before I start putting a second one in, right? And it has to do with complexity. Electrons hate each other. They want to get as far away from each other. We talk about this thing called spin. It's tricky, but we pretend that it's not. All right. So how do we do configurations. Let me go to a new note for a minute so I can just how would I do a new note? Here we go. Let me just go to a new note for a minute. Okay, so let me refresh your memory about the periodic table. All right. So this is S, this is P, this is D, this is F. And essentially what we're doing is we're putting electrons in, all right? And let's start with the first 10 atoms. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Element number 1 is hydrogen. Element number 2 is helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Okay. So this is the atomic number of the element, which means that's the number of protons, but it's also the number of electrons, right? And so hydrogen is right up here, right? So the question is, where is that one electron? Well, where that one electron is in row 1, and it's in an S block. So we would say the configuration for that first electron for hydrogen is 1s, and we put a little 1 next to it because there's only one electron, right? Helium, which is over here, but really should be there, has one more electron. So its configuration is 1s2, right? So we're basically just saying when we write electron configurations is we're telling you how many electrons something has and what orbitals those electrons live in. Where do they live? So hydrogen, if we drew a picture, here's the nucleus, here's the electron in the 1s. We drew a picture of helium. Helium's nucleus is a little more complicated, and here are the 2 electrons. They're both in that first energy level. They're both in S. And they're moving somehow. They hate each other. They're trying to stay away from each other. But if we go to lithium, right, something changes, right? Now we're here. We're in the next column. So lithium has 3 electrons, right? By the way, you might have noticed also that every successive atom is the previous atom plus 1 electron, right? So when I take hydrogen, I add 1 electron and 1 proton, I get helium. When I take helium, I add 1 proton and 1 electron, I get lithium. There's some neutrons in there as well, but we're not really worried about the neutrons. Go from lithium to beryllium, I add 1 proton, 1 electron, right? And those electrons have to go somewhere. The protons always go in the nucleus. The electrons always go in orbitals. And the periodic table is set up to help you understand where the electrons are. So lithium, to get to lithium, I have to go through hydrogen, I have to go through helium, and then I'm at lithium. Well, this guy right here says I've gotten through with helium, so 1s2, and then I've got lithium right here. He's got 1 more electron, 2s1. So I've added 1 more electron to make lithium. If I went to beryllium, which is right here, beryllium has 1 more electron, so it's 1s2, 2s2, right? So I've added 1 more electron to beryllium. This thing that I'm drawing every time is what we call the electron configuration. It's just a notation for telling you where pretty much every electron in an atom is, starting from the nucleus, right? And the thing you should remember is that every atom looks just like the atom before it plus 1 more electron, right? That's super important. And it's basically true, right? Because every time I add an electron, it has to go somewhere. In the case of going from, so that was helium that we just drawn. If I want to go to lithium, I have to go to the next energy level, right? Because I added an electron down here. So that would be lithium, 1 more proton, 1 more electron. I go to beryllium, 1 more proton, 1 more electron. But now where life gets a little complicated, if I'm going to go from beryllium to boron, the next electron goes into a p orbital. All right. So the next electron would have to go to p. So boron looks just like beryllium, 1s2, 2s2. But now the next electron is in a p orbital, 2p1. All right. And you can see that the next successive electrons are going to be putting in all go into p orbitals, right? The next 5 electrons all go into p orbitals. So carbon, 1s2, 2s2, 2p2, nitrogen, 1s2, 2s2, 2p3, halfway there. Oxygen, 1s2, 2s2, 2p4. Oxygen is 4 into this block. Fluorine, 1s2, 2s2, 2p5. And then neon, 1s2, 2s2, 2p6. Right? So the configuration is pretty straightforward, but there's some things that you should kind of pay attention to with configurations. And let me pick a different color here. Okay. This guy right here and all of these guys right there, remember those are noble gases. They're not really reactive, right? And the reason they're not reactive is if you look at them, you'll notice that they're full, right? I don't have room for any more electrons. The p orbitals are full. They can only hold 6 electrons. So it's full. Helium is full. So the reason these guys have stability, these are stable noble gas, is because the outer or valence shell is full. All right. That's going to govern a whole bunch of things that we learned about earlier when we talked about, well, things want to form ions or things want to form bonds. How do we know how many electrons something has to gain or something has to lose? When we looked at the periodic table, I just said, okay, this is group 1, it loses 1 electron. But we didn't really talk about why. Why does it only lose 1 electron? Or why does it only gain 1 electron? And to help make sense out of that, I'm going to introduce something called an orbital notation, which looks a lot like electron configuration. So I'm going to turn this sideways, and it's going to give me a little bit of room on the bottom to rewrite this. So I'm going to write hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. I'm going to write neon. All right, this was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember, that's the atomic number, the number of electrons. But now instead of writing 1s, I'm gonna put a dash and I'm gonna write 1s under it. Then do the same for helium. For lithium, I'm gonna write 1s and then 2s. For beryllium, I'm gonna write 1s and then 2s. Boron, I'm gonna write 1s, 2s, 2p, and the p's have 3, and I'll stop there for a minute. So basically what I'm doing is I'm not writing the configuration per se. What I'm doing is I'm giving just a line where I can put electrons in, all right? This is called the orbital notation, by the way. And orbital notation actually shows you individual electrons, all right? Now, how do we indicate electrons in an orbital? I mean, when I drew the picture up here, I just used little dots. The way we indicate electrons in orbital notation is we say that an electron is represented by an arrow. And you can have like a fishhook arrow with just one arrow, or you can have an arrow either way. Electron looks like that. That's how we're going to indicate that there's an electron in an orbital. And in real life, remember, things are moving. We don't know how they're moving, but we know they're moving. And electrons behave as if they were spinning, right? How do we know they behave as if they were spinning? You know, again, it has to do with magnetic field and how they behave in a magnetic field. Are electrons really spinning, right? So if this was an electron, is it really spinning on its axis? I don't know. I've never seen an electron, so I don't know if it's spinning, but it sure behaves like it is, all right? And so what we do is, in order to get 2 electrons, right? 2 electrons can fit in an s orbital. We say that they're spinning in opposite directions. So any orbital, this is an orbital, this is an orbital, this is an orbital, this is an orbital. Any orbital that has more than 1 electron, they have to be spinning in the opposite direction, right? And that, if I went back to that, if I went back to the PowerPoint, oops, let me undo that. That's part of this guy right here, the Pauli exclusion principle. 2 electrons per orbital, but must spin in opposite directions, right? Again, this is not something that you would just think of and come up with out of the blue. It's a result of quantum calculations. It's a result of what we've observed about electrons. We know that an orbital can hold at most 2 electrons. We know electrons are negative. They hate each other. But if they spin in opposite directions, oops, sorry about that. If they spin in opposite directions, why can they get near to each other? Let me digress just briefly, right? Because this is actually kind of interesting. So if you have an electron, which is charged, and you spin it, so let's say it's spinning on its axis like a top, what it does is it generates a magnetic field, all right? Anytime you take a charge and you move that charge, it generates a magnetic field. So when the electron's spinning, it's actually behaving kind of like a magnet. So it'll have a north and a south pole, right? And if you take another electron, and put it right next to it, these electrons don't like each other. This is a negative, this is a negative, and you might remember, we mentioned this, they repel. Negative charges hate each other. They don't want to be anywhere near each other. So how can you get 2 electrons close to each other in an s orbital, right? Well, they're moving, so they could try to avoid each other, but eventually they're going to see each other. How do they do that? Well, the way nature accounts for that is through something called spin, and we let this one spin in the opposite direction, all right? So it's spinning that direction, and we put that arrow pointing down. And what happens is if it spins in the other direction, the magnetic poles are reversed. And so these hate each other because of the negative charges. Let me undo that. That was a bad color to put in there. These guys hate each other because of the negative charges. That negative charge makes these guys want to repel. But the fact that there's a magnet here, those guys don't want to repel. Let me undo that.
I have a question.
Yep.
So the electrons in the current is what cause B fields in electromagnetics?
Yep, absolutely. So if you're talking like it's actually true in a magnetic material. Why are some materials magnetic? It's because they have unpaired electrons, and so they can create magnetism in a material. If you have like an electromagnet, like if you take a coil of wire, right, and connect it to a battery, the current will flow through this, and the fact that the current is the flow of electrons, the electrons aren't spinning, but what they're doing is they're moving in a straight line. And anytime you move a charge, it's part of Maxwell's equations. Anytime you take a charge and cause that charge to move, there is a magnetic field associated with it at right angles to that movement. It's just part of nature, how nature works. And so anything with a charge, doesn't matter what it is, even if it's your hair on a dry day, if you run really fast, you're setting up a magnetic field. It's really small, but yeah, that's the relationship between electricity and magnetism. And so it's true in the atomic sense as well. This is a north pole here. Why is that not right? I'm going to turn my pen off. So this is a north pole right here. So whereas these guys cause the repulsion, these guys are attracted to one another. In reality, this repulsion is somewhat stronger than the attraction, but the fact that there is some minimization of that repulsion allows you to get 2 electrons relatively close to each other in an orbital, all right? And so that's why when we go back to this orbital notation picture right here, as we start to put electrons in, we're going to put them in, right? So hydrogen only has 1 electron. We just put 1 electron in hydrogen. But helium has 2 electrons, and they're both in the 1s. And so the way we indicate that is we put 1 spin up and 1 spin down. And that's how we would say it: spin up, spin down. And if you did it like this, and like this and like this. If you actually make it an arrow rather than a fishhook arrow, I don't really care. It doesn't really matter. But most people, just do that half arrow, spin up, spin down, right? So lithium, we'd have 1, 2, 3. And I think it's important that you watch how I put those electrons in, because that's part of one of the rules as well. So I'm going to erase that. I'm going to go back and do it again. And maybe you guys can watch what I'm doing here. So when I put these electrons into lithium, right, you're looking at lithium. Let me get rid of these extra lines here. So when you're looking at lithium, lithium has a 1s orbital and a 2s orbital. And when you're looking at it, lithium has 3 electrons, right? But watch how I put the electrons in. I put 1 here, then I put 1 here, then I put the third one there. And you might say, well, so what? That's no big deal, of course. But if you have 2 gashes, which we'll call 1s and 2s, here's one way you can put the electrons in. You can go 1, 2, 3. That's one way to put the electrons in, right? Okay, but the if I go back to the PowerPoint, all right, degenerate orbitals, equal energy orbitals, are filled with 1 before pairing occurs. And so if I go back to the thing I was just working on, these are not degenerate orbitals, right? This is a 1s, which is lower in energy than a 2s. So I have to fill this one before I put anything in here, right? In the end, if you get the right answer, it's not a problem. But later on, when you have more complicated atoms, it's going to become an issue. So it won't show up until we get to the P. So let's continue on here. So beryllium, 1, 2, 3, 4, right? That's the configuration of beryllium. I also want to point something out a little bit that may or may not be something you should be thinking about or have been thinking about. So you might remember, and I'm going to refresh your memory again, when n equals 1, you can have S. When n equals 2, you can have S and P. Equals 3, you can have S, P, D. When n equals 4, you can have S, P, D, and F. You can have, right? So when I'm at lithium, right? When I'm at lithium, I have the second energy level available to me. That means these p orbitals exist. They're just regions of space, but potentially they exist, and I potentially could put electrons in, but I don't, because I only have 3 electrons. Lithium only has 3 electrons, and starting at the nucleus, the first thing I encounter is the 1s, so I put 2 electrons in. If I keep moving out, the next thing I encounter is the 2s, right? Now you might say, well, isn't 2s and 2p, aren't they both in the second energy level? Aren't they degenerate? That's a good question. No. These guys are p orbitals. They're degenerate. They're all equivalent energy. This is an s orbital. Even though they're in the second energy level, s orbitals are slightly lower in energy than p orbitals. What that means is s can get the electrons closer to the nucleus than the p, right? So these orbitals are here. We just never draw them because I don't have enough electrons to put in them. But it's going to become important when we start to talk about the formation of ions. All right, so I just wanted to throw that out to you. All right, so next one is boron. We put the first 2 electrons in. That takes care of 2 out of the 5. I got 3 more electrons. Next 2, I've taken care of 4 electrons. So I've used 4 out of the 5 electrons that boron has. I've got the next one. I've got to put it in one of these p orbitals. Which p orbital do I put it in? Right? At this point, it doesn't matter. All right? It really doesn't matter. You got 3 of them. One of them's the px, one of them's the py, one of them's the pz, which is which. And when you draw stuff like this, you don't know. So we'll call this 2px, 2py, 2pz, right? They're all identical. There's no difference in any of them. And so you've got 1 more electron because boron has 5. Where does it go? It doesn't matter where you put it, but you should be consistent. I always put it in the first available spot. Could you have put it here? Yep. Could you put it here? Yep. Doesn't matter. You could do that if that's your desire. What you need to do is you just need to make sure that you are consistent when you start doing things. All right. So let's go back carbon, all right? So carbon, now I'm gonna have to put my pen back to black. All right, so before I do the carbon, all right, let's go back up and look at the notation for carbon. Carbon was 1s2, 2s2, 2p2. So if I did this, if I wrote this out already, it should be pretty obvious what the orbital notation is going to look like. The 1s is full, the 2s is full, and the 2p has 2 electrons, right? But this is where those other rules start to come into play. I have 2 electrons in the p. Where am I going to put them? Well, 1s is full, 2s is full, 2p. Now I've got 2 electrons to put in. Here's one option. That's not right. You can't do that because the rule said when you have equal energy, you got to split them up before you can pair anybody up. So that's a valid answer for the second one. That's a valid answer for the second one. Right? You can put that second one in any of the other open spots, but I always just follow the pattern, just put the second one there, right? And then if we went on to nitrogen, the configuration for nitrogen is pretty straightforward as well. Give myself a little bit more on the page. So nitrogen, we got 2 electrons out of the 7, 4 electrons out of the 7, 5, 6, 7. There's the 3rd electron of the 7, right? Now, before I move on, I want to point some things out. When we talked about nitrogen forming an ion, does anybody remember what charge nitrogen liked to form? Anyone remember if nitrogen forms an ion, what charge did it like to form? Anyone? Think about the periodic table. Think about where nitrogen was in the periodic table.
Negative charge.
Pardon?
Negative.
Yeah, absolutely. It wants to form a negative, but what number?
-3.
-3, absolutely, you're right. Why does it want to form a -3 charge? Well, look at the orbital notation for nitrogen. How many holes do you see? Easy question. I see 3 holes, right? So when you're looking at the orbital notation, it becomes pretty obvious right away why nitrogen likes to form a -3 ion, because if I put an electron there, an electron there, an electron there, I formed N-3. But what does this now look like? What atom has this configuration? Not what ion. So this is the nitrogen ion, but what atom has that configuration? Well, what atom is 3 over from nitrogen? Somebody is, let me put the chat back on. Neon, absolutely, Nick, you nailed it. This is the same thing as neon, right? That's why noble gases are really important, because they have a full stable configuration, and any other atom that's going to react chemically is going to react to try to look like a noble gas, right? So if we go down to the bottom and do neon, so 1s, 2s, 2px, 2py, 2pz. Neon's got 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this, in fact, is what the nitrogen -3 ion looks like. It should come as no surprise to you guys that oxygen, I try to change the color. 1, 2, 1, 2, 3. Here's oxygen. 1, 2, 3, 4, 5, 6, 7, 8. All right. Oxygen has a gap here and a gap here. How many electrons does oxygen like to accept in order to form an ion? Or what's the common ion of oxygen? Oh, what? -2. -2, right? Why is it -2? Because it's missing 2 electrons. If you gave it those 2 electrons, it would look like what?
2 over.
Which is
Ne.
Ne. Wow, that's really boring. Okay. Any guesses what fluorine -1 is going to look like without me even drawing it? Fluorine -1 is going to look just like
Ne.
Ne, right? So there's a word for that. I'm going to write it here. Isoelectronic. Remember this word? We talked about this prefix before. Remember what iso means? No?
Isolate.
Isolate. Oh, I don't think iso is part of
Isotope.
Isotope. Okay, we talked about isotope. What does the iso in isotope mean?
Variety.
Not equal.
Means the same.
It's oh.
Isotopes are the same element with different numbers of neutrons. So isoelectronic means these guys have exactly the same configuration. N-3 is the same configuration as neon. O-2 is the same configuration as neon. F-1, same configuration as neon, right? They're all the same. Why are they same? Because neon is stable and chemistry is all about stability. So these guys are over on the right. These are nonmetals, and nonmetals always gain electrons to become ions. What about lithium? Lithium's a metal, right? Do metals gain electrons to become ions? Remember? Yes or no? No. Metals lose electrons, right? So lithium, because it's in group 1, what ion did lithium form? Anyone want to take a stab at that? Lithium formed lithium plus what? It's in group 1. Lithium formed lithium plus 1, right? Which means it's getting rid of that electron. Gone. What does that look just like if I get rid of that one electron? What is it isoelectronic with? I took one electron away. So if I take one electron away, which way do I move in the periodic table? I move backwards one element. So what's the element right before lithium?
Helium.
Oh, what's true about helium? Helium's a noble gas. So lithium loses an electron, becomes positive, and looks just like the noble gas before it. All right. Beryllium. Beryllium, we didn't do much with beryllium, but what type of ion does beryllium form? It forms a plus ion, but plus what?
2.
Plus 2. So beryllium loses these 2 electrons, and it looks just like helium. All right. Isoelectronic. So one of the things that's important to realize about the periodic table is it gives you a clue as to whether something's going to want to gain electrons or lose electrons. It also tells you how many it wants to gain or lose, right? Because of how electrons populate those orbitals, right? These guys in the S block and P block are super easy. Remember the D block was really fuzzy and hard to predict? Sometimes they lose 2, sometimes they lose 3. That's because d orbitals are really big and really mushy, and they tend to overlap, and the chemistry gets kind of confusing, and it's not so easy to predict, at least not easy to predict in Gen Chem. All right. But if we went to the next level of the periodic table, let me see if the slides have that periodic table next. We'll talk about that a little bit later. We did electron configurations. We did this. So this is orbital notation. Did that. Let's see if I had a periodic table in here. I don't. All right. So I believe that I might have, in the notes that I sent you, had a periodic table. Notes yesterday. You know what? It's probably going to be easier by name. No, April 16th. Right? Nope, that's today. No, April 14th. Was I able to get a periodic table in this? I think I did. I think I was able to get a. There we go. Okay, so if we have a periodic table, Okay, if we've got this periodic table, now we can start to think about, okay, what's going on here? So imagine we just talked about lithium. Lithium and beryllium lose electrons and they look just like helium. Sodium and magnesium also lose electrons, but what do they look like then? You can just shout it out because I can't see my chat. So if these guys lose electrons, sodium's going to lose 1 electron, right? Everything in group 1 always loses 1 electron to form +1. So if sodium loses 1 electron, it's got how many electrons? 10. What's element number 10? Neon, right? So sodium loses an electron to look like neon, whereas fluorine gained an electron to look like neon. Right? It's always about looking like these guys. These guys are like the divas of the periodic table. So chemistry happens to make atoms look like noble gases. They have especially high stability, right? Why are they stable? Because atoms like full shells, right? Even if they have to lose or gain electrons to get those full shells, there's something special about having a full shell of electrons that makes the atom stable. And so that's the underlying reality of why the periodic table is set up this way. And it helps you to start to think about, okay, why is this guy going to gain electrons? Why is that guy going to lose electrons? And then how do we write that? So the fact that we're writing these things, as electron configuration or orbital rotation, that's kind of just a shorthand for you to be able to see where the electrons are and what's happening with them. But in reality, right? So in reality, something like oxygen or neon, all we really care about is the highest energy level electrons. We don't really care about the core ones. And so there's a couple of other terms that we might throw out there, right? So let me pick sodium. All right, so sodium is element number 11, which means it has 11 protons and 11 electrons. If I was going to write the configuration for sodium, I would start at the nucleus and work my way out. And I would use the periodic table if I were you, because it just makes life easy, right? But I kind of know the pattern that these things follow, right? So if I have 11 electrons, I'm going to fill up the 1s first, so I get 1s2. Then I'm going to go to the 2s, and I'm going to fill that up. And then I'm going to continue moving across the periodic table, and I'm going to get to the 2p. They can hold a maximum of 6, and I know I'm going to fill them up because sodium has 1 more electron in that next thing. And again, I know that because sodium is, right, 1, 2, 3. Sodium is right here in the periodic table. It's in the 3rd energy level, and it's the first into the S block, right? That corresponds to the position of sodium in the periodic table. All this other stuff is basically a placeholder, right? This is just getting me to this place. This does not define the chemistry of sodium. This defines how Na reacts, all right? It means Na forms +1 compounds. It means it loses an electron. It means the formula is going to be NaCl and not Na2Cl, right? Its position for the last electron, right? And remember, we had a name for that. That's called the valence electrons. Oh, that looks like valency. So this is the valence electrons. And again, to define valence electrons, they are the highest energy level electrons. Right? This is the energy level right here. So sodium has 1 valence electron. Magnesium, which is right next to it, has 2 valence electrons. Oops. Sorry about that. Okay. By the way, there's some shorthand we can do. This stuff all right here, right? If I add that up, 2, 4, 10, what element has 10 electrons? That would be neon. So I can write this configuration in another shorthand way. I can write 1s2, 2s2, 2p6, 3s2, or I can write neon 3s1. Those are equivalent. Those are exactly the same thing, because this guy right here is what we call the noble gas core. Right? You might call it the kernel. It's not reactive. This part of the atom doesn't take part in any of the chemistry, right? I don't mess around with these electrons when I'm doing sodium chemistry with sodium. This is the only electrons that sodium has for chemistry. I don't mean to imply we can't mess around with these electrons. We can, but it takes a lot of energy to start messing around with these electrons. Why? Because it looks like neon, and neon is really, really stable. So we don't mess with those electrons per se. Can you? Yes, you can mess with those electrons, but you're talking on the order of energy like X-rays rather than simple chemical reactions. So it's substantially more difficult to get those guys to work and to do some chemistry, right? We could also do the orbital notation for this guy. We could also write, sorry about that. We can also write Na, 1s, 2s, 2p, 3s, and again, follow through. Notice again, I put 1 in each of the p's before I fill them, and then there's 1 electron there. And you can also write this same thing. Oops, sorry, I didn't want to write Na. I wanted to write neon 3s, and just put the 1 electron in. So those are all legitimate ways to represent where the electrons reside in an atom, right? This is still an electron configuration. This is an orbital notation. This one uses the noble gas core. This one does not use the noble gas core. They're all the same. This is the easier way to do it. To me, it's more esoteric because it shows that you understand that these electrons do not take part in any of the chemistry, right? And you can do that for something at the other end of the periodic table as well. So if we were, for instance, talking about, let me go back to the periodic table that we were just looking at. So if we were talking about, let's pick phosphorus. We haven't done a whole lot with phosphorus. What would the configuration for phosphorus look like? All right, here's phosphorus right here. Right. Well, I can see that phosphorus ends in a p block. If I go backwards from phosphorus, I go to this, and I keep coming back, and up phosphorus, the nearest noble gas is still neon for phosphorus. So I could write neon, which takes care of all the electrons up to here, and then I would just have to write 3s2, 3p1, 2, 3. So phosphorus, if we picked to do phosphorus, it would be neon, and then it would be 3s2, 3p3. I'm going to go back to the periodic table. Go back to the periodic table, like I said. I'm going to try this one more time. We go back to the periodic table, right? And you can see we're still in this third energy level right there, still the third energy level. We're 1, 2, 3 into that. So the periodic table is incredibly useful for writing configurations, right? And I would strongly recommend that you don't try to memorize anything. There's rules out there. There's little figures you can draw with arrows trying to figure out what electrons and what order they fill in. Don't waste your time with that for a couple of reasons. One, the quizzes and exams are going to be open book, right? So to be honest, you could just look it up, right? But there's no sense in memorizing a device when you have the periodic table, which is designed to help you be fluent in that, all right? And then you can look again at phosphorus, and you can see phosphorus and nitrogen are in the same area. Nitrogen formed a -3. Guess what? Phosphorus forms a -3 as well. Why? Because it's 1, 2, 3 away from the next noble gas, right? And so if phosphorus forms an ion, if we want to form an ion, the p-3 ion, it became -3 by gaining 3 electrons, right? So that means now that becomes phosphorus, P minus 3 is neon, 3s2, 3p6, which is exactly the same as argon, right? It's isoelectronic with argon. And that's what we're shooting for. We're always trying to make a noble gas when we make an ion, all right? Okay, I said I wasn't going to yap for the whole time, so I see this is probably a really good time for me to stop and see if anybody has any questions. Do any of you have questions? I'm looking around and I don't see any questions.
Professor, I have a question.
Yes.
So you always have to include a noble gas?
No, you don't have to include a noble gas. If I say give the configuration with the noble gas core, you have to include it, right? So if the question said, give the configuration for nitrogen and include the noble gas core, then you'd have to include helium and then write the rest. But honestly, Sammy, if I were you, I would always include the noble gas just because it makes it shorter and easier, and it shows me that you understand that noble gas that makes up the core of that atom is really unreactive. It's just the outside electrons. And when you write the noble gas, all right, so let me share my screen again. When you write it in this fashion, all right, when you write it in this fashion, it shows you clearly, right, that this is a 3, and you know that the biggest that can be is a 6. So I already know that that's not full. I already know I can put some electrons in there. Or if you wrote it this way, 3s, 3p. Honestly, orbital notation is way more useful than electron configuration. So if you had drawn this orbital notation, you could clearly see right away, oh, you know, there's a hole there, there's a hole there, there's a hole there. So that means that guy's probably going to form a -3 ion, right? You might be also tempted to think, well, it's got 3 holes. Why can't I just put 1 electron in there and make a -1 ion? Well, the rule is you want to look like a noble gas, right? And the way to look like a noble gas is to put 3 in there, right? So that's something that you kind of got to remember. If you have gaps to get to a noble gas, you got to fill them all, and that gives you the most common ion of that particular species. So Sammy, if I were you, I would always use the noble gas core because it gives a lot more information. Okay?
Okay, thank you.
Sure. Any other preguntas?
Right,
Yeah.
another question.
Yep, go
So,
for it.
for example, if you ask me to write electron configuration for sodium,
Mm-hmm.
then I'll have to write Ne and then 3s1, right?
Boom. Yep, that just happened. You nailed it.
Oh, okay, got it.
Yep, you go to the closest noble gas. So for instance, argon, phosphorus, the closest noble gas is neon, but it also has helium inside of that. So would you write helium and then all that other stuff? No, you pick the closest noble gas. So you just go backwards in numbers until you find a noble gas. That's the core of that particular element, right? Backwards or forwards, depending on what kind of ion you're making.
Yes, yes. So
Yep.
if you don't include a noble gas, then you have to start from the top, right?
You got to start from 1s. Yep.
Okay, got it.
And so, okay, the ones I've done are no big deal, but if you think about the periodic table, let me share my screen again. So let's go back to the periodic table. Let's say I asked you to do like, my pen is on. No, my pen's turned off. Let's just say for fun, I asked you to do tellurium. How many electrons do you got?
52.
You got 52 electrons. So you're going to be, let's see, to get to this point, to get to 52, you got to go through 1s2, 2s2, right? I'm just following through the periodic table, 2p6, then I go 3s2, then I got 3p6, and I'm only to this far so far. I'm only to 18 so far. I got to keep going all the way to 52. What's after 3p6? 4s2. What's after 4s2? I got to do this section right here. What's this section? Anyone remember?
D.
D. Which D is it? Where do the D's start? 1, 2, 3, 4. What number has to go in front of it? This is the trick question.
Is that 1?
Well, let's remember what it said. In n equals 1, you can have S. In n equals 2, you can have S and P. N equals 3, you can have S, P, and D. This is the first time we've encountered a D, so it has to be 3D. I went all the way across, so that's 3D10. What do I encounter after 3D10? I encounter this row. It's a P row. Which P row is it?
P4?
Yep, it's 4P. So that's 4P6. That gets me to 37. So what's next? What's after 4P6? You can't see it. My writing is on top of the periodic table.
5s2?
Yep. Then next is 5s2. 38. Then I go through 39 through 48, which is now 4D10. Oh my gosh. And then I go 1, 2, 3, 4, and I'm at tellurium. So 5P4. That's the configuration for tellurium. That's a mess, right? Or you can write, what's the closest noble gas? It's krypton, right? So you could also just write, let's see if I got a little bit of room here. I do. Oops. You could also write krypton, which is the noble gas, takes care of 36, then 5s2, right? Then 4d10, 5p, what did we say? 5p4? 1, 2, 3, 4. Yep. So that's the configuration for tellurium, and the one I wrote above is the configuration for tellurium. Which one do you want to do? It doesn't matter to me if I don't specify, but I will tell you that you're more likely to make a mistake on this one, right? You're more likely to leave something out. The longer it gets, the more chances you have to make a mistake. So it's always better to write the core. And again, if you write the noble gas core, then you've got some information about just the valence electrons, just the valence electrons. Now, these all look like valence electrons. Well, that's a trick question. Valence is really the highest energy level electrons. So are these officially valence electrons? What do you think? This is a yes or no question. What's the highest energy level in krypton? I mean, in tellurium. Not a trick question. The highest energy level is 5, right? Those are the valence electrons in tellurium. Even though it's got this d orbital, it's a 4d. So those are not the valence electrons. These are the valence electrons. So tellurium has 6 valence electrons, and it's just like anything else in that position. It's going to want to gain 2 electrons to become xenon. So tellurium, the common ion of tellurium would be Te -2. That would be the ion it would like to form. Right? So the periodic table is incredibly useful in terms of trying to do configurations and orbital notation. And I believe at this point, I've given you a bunch of information that will allow you to do. So if we go to week 10 resources and activities, and we looked at, was it week 10? Or was it week 11? It was week 11. Sorry, I apologize. So if we go to this one, right? Am I sharing my screen? I'm not sharing my screen. I apologize. Allow me to share my screen. I'm looking at it and I keep forgetting that I'm not sharing my screen. So share my screen. So if you go to week 11, let me back up a little bit. So we're in week 11. We go back to week 11, electrons in the atom and periodic table. If you go to week 11, resources, activities, and keys, and then if you go to electron configurations, Lewis dot structures, we haven't gotten to dot structures, but you can do some of this now. So if you go to this, right, it's very similar to what we're talking about alpha principle. You'll notice that this has them going up this picture is designed to help you understand that a 1s is lower in energy than a 2s, which is lower in energy than a 2p, right? You could write them all in one line, or you can make them going up and down like this. It's not that complicated, right? And so we've done some of this already with lithium, right? Hydrogen, helium. Lithium has 3 electrons, so you'd have 2 electrons here and 1 electron here. So there is some practice in terms of these sorts of things. So you do have some things that you can practice. What we haven't done is this next thing about dot structures, and we'll talk about that on Tuesday when we get together next. So you'll be able to do a good chunk of this particular worksheet if you so desire. And you, of course, have homework on sapling that you can work on and those sorts of things. Okay? Are we all good? Everybody's happy? I don't see any questions.
You're not going to collect any of the worksheets?
I am not. I'm going to solely use your homework to do that sort of thing, because I haven't collected any worksheets yet at all. I don't think it's right for me to all of a sudden just start collecting things now. In the past, you had the opportunity to work together with your peers, and I could come around and give you feedback on those particular worksheets. But I think that's even more complicated with this, even though you might be in a group working on a worksheet together with someone virtually. I don't know. I find that odd. So what I'll do is I'll just say basically we're done for today. Take some time to work on that worksheet. If you run into issues with it, 2 things. The key is there, so you can look at the key, and I'm always available. So if you wanted to get something, just message me either through email or send me a text, and I'll give you help as soon as I can. Okay?
Yes, Professor, I have another question. Sorry.
Sure, no problem, Sammy.
So are you gonna put up grades on titanium, or?
Am I going to post the grades? Were you here at the beginning when I explained how to calculate the grade?
Yes.
Yeah, so that's what you should do. I am not going to, because when I looked at titanium, the grading thing had already been kind of set up, and I'm not smart enough how to figure out how to change it. And so I'm officially not. What you can do is, if you have all your scores, you can just use that formula, and I recorded this so you can follow along on Excel or online to do it. In fact, I can share this Excel folder with you guys. So this file that I created via Excel, let me share my screen again. So this file that this file that I created via Excel, what I can do is I will share this file with you guys, and all you have to do is put your numbers in here. You just have to put your homework percent from sapling, put the scores that you got from the quizzes, and in order to get it to do the math for you, all you have to do is grab this corner and drag it down. All right. There's no data in these columns over next to it, so it can't do the calculation. All right. So once, like for instance, let's say you brought this home. You're like, okay, I downloaded this. I want to put my grades in. So let's say your homework average is an 88. Let's say you quizzes like 16. Let's say you aced the second quiz 30. Let's say you aced quiz 3. Quiz 3 is supposed to be out of 30, not 3. Let's say you aced this quiz and you actually, you know what? Now I realize, looking at this, that formula needs to be tweaked a little bit. Let's say on this next quiz you got 25. Let's say that you got I don't know, a 95 on the exam, and let's say you got an 85 on the exam. All right. Okay, so exam averages are fine. So how do you get these formulas to go here? Just grab this corner and drag it down, and it will automatically copy the formula and prorate it to the data that's in this column. Same here. If you grab this and bring it down, it'll take that particular thing and do the data here. The quiz average. All right. I think I need to do the weighted average here instead of just the individual average. Now I'm looking at, because the quizzes weren't all worth the same value. So this should really have been, this is actually not the right way to formulate that formula. This should be equals, we'll just do it simply. This plus this plus this close parentheses slash, what is that, 80. That's the real average of your quiz. Okay, let me just do this, copy that down. That's better. Now that's a real average. And then these were the same basis because they were the same 100 points, so that you can just average those together. But see how that changed the value of this person's score, right? Because their quiz averages were their quiz average, actually, that seems a little low, 95, 95, 88. That should not be a 77 then. Let me redo this formula. All right, so we said that this should equal open parentheses. All right, that first box was homework equals this box asterisk, and we said homework was this box 0.25, so that's 25%. A3 asterisk 0.25 plus the quiz average plus this. Oh my gosh. Oh, what was that? 0.25 plus this. And we said the quiz average was 0.15 asterisk 0.15 plus this asterisk 0.6 close parentheses. Why is it coming up as 77? That seems low. Oh, that's why. This is giving it as a decimal, not as an actual number. There we go. Okay, that's better. So that person has a 90 average. And then if you were to do this, you just grab the corner and drag it down. Not that. You grab right here on this corner and drag it down, and it gives you your value, right? So let's try this one more time. Let's say you go in here and your homework was a 99. And let's say your quiz, you didn't do so good. Let's say you got a 15 on that quiz. And let's say you did a 25 on this quiz, and let's say you did a 25 on this quiz, and let's say your exam 1 was a 72, and let's say your exam 2 was an 88. All right, these things will not automatically populate. You have to highlight the box, grab the corner and pull it down, and it will copy the formula there. And you can, by the way, you can do these together. You can do as many boxes as you want. I'll just do them one at a time. Drag it down, and then the thing has to be right on the corner, and for some reason it's not liking me. There it is. You got to have that black crosshairs when you drag down, so that person would have an 84 average. So Sammy, you think you can do that?
Yes, got it. Thank you so much.
Okay. So what I'll do is I'll just save this to my desktop. Save as Chem115 grade calculator, and I'll post that, or I'll just email it to all of you. I'll probably just post it on Titanium. The thing you guys got to remember is that the syllabus did say you can drop one quiz. So if you want to drop your lowest quiz, that's fine, but the formula will be off. So you have to tweak the formula. You just have to decide which quiz you're going to drop. Doesn't matter to me. Okay. And that would be the case of that. So let me stop sharing. All right. Any other questions? You're going to make me go to 7:30 anyways, aren't you? I don't mind. I like spending time with you guys. Any other questions? No? All right. It's been a pleasure. Email me, text me if you guys have questions. Otherwise, I will see you on Tuesday. Okay? Everyone good?
Thank you, Professor.
Yeah. All right. Take care, guys. Nice
Good night,
seeing you all.
Professor.
Good night. Take care. Enjoy your weekend. Stay safe. Bye-bye.